Buckle up, everybody, because today we are diving deep into the realm of black
Oh,
holes.
yeah. Those mysterious objects in space that have captured our imaginations for so long.
You know, the ones that make even the laws of physics as we know them, well, kind of break down.
They really do.
Yeah. And we're using Physics Fundamentals Explored as our guide for this deep dive. It's pretty wild what these things can do. We're talking about regions in space where gravity is just so incredibly strong that it warps the fabric of reality.
Yeah.
I mean, think about it. Even light can't escape these things. It's like, what?
Like, whoa.
Right. So imagine like a cosmic vacuum cleaner, but one that's swirling so fast it pulls in everything around it, even light.
That's a pretty good way to put it, yeah.
That's kind of what we're dealing with here when we talk about black holes.
Yeah, and what's really fascinating about black holes is they challenge our understanding of physics.
Right.
It's like, how can this even be? You know, how can something have so much gravity that it even traps light?
Exactly. It's like a glitch in the matrix or something.
Yeah. They form these black holes when massive stars much bigger than our sun, they die and they collapse under their own immense gravitational pull.
Okay, so picture this. You got this giant star, way bigger than our sun.
Yeah.
And it's like imploding in on itself. What happens next?
Well, that's where it gets really, really interesting.
Oh, I bet.
The star's entire mass gets squeezed into this unbelievably tiny point. We call it a singularity.
Singularity.
Yeah, and its density. It's theoretically infinite.
Infinite density. That's like, I can't even wrap my head around that. That's just crazy.
It really is.
It's like beyond our comprehension.
Yeah. Now, surrounding the singularity is a boundary, and it's called the event horizon. It's kind of like the point of no return.
Okay, so the point of no return. So like, once you cross that line, there's no coming back.
Exactly.
Like, what's a good analogy? Like falling off a cosmic waterfall or something.
Yeah, something like that. Once something crosses that event horizon, it's inevitably drawn towards that singularity. Even light.
Even light. Wow.
And that's why we call them black holes, right?
They're black. Like nothing can escape them.
Yeah.
So it's not just that they're dark. It's that they're like these cosmic vacuum cleaners.
Yeah.
Just sucking in everything around them.
They are.
All right, so we've got these objects with infinite density, warping space-time, and gobbling up anything that gets too close. Now tell me, are all black holes created equal?
That's a great question. And the answer is no. You know, we've actually observed different types of black holes out there.
Really? Oh, this is cool.
There are these things called stellar black holes. They're formed from the collapse of individual stars, and they're typically a few times heavier than our sun.
A few times heavier than our sun.
Uh-huh.
That's already hard to imagine.
Oh, yeah.
So that's like one type. Are there even bigger ones?
Oh, absolutely.
Okay.
We have these things called supermassive black holes.
Supermassive.
Yeah. And these reside at the centers of galaxies, including our own Milky Way.
What? So our entire galaxy is revolving around a supermassive black hole.
It is. These are the heavyweights. Millions or even billions of times greater than our sun.
That is wild.
Isn't it?
All right, so stellar, supermassive. You also mentioned earlier intermediate and primordial black holes. What about those?
Those are still quite mysterious.
Oh, really?
Intermediate black holes, we think they exist somewhere between stellar and supermassive.
Okay, kind of in between.
Uh-huh.
Got it.
Yeah. But they're much harder to find. Primordial black holes, well, they're still hypothetical. We haven't actually observed them.
Okay.
But scientists believe they might have formed way back in the very early universe.
Oh,
And these could be incredibly small, maybe even smaller than an atom.
okay, so we've got this whole spectrum of black holes out there,
Yeah.
from tiny ones that might be smaller than an atom to these galactic behemoths. But here's what I don't get. If they're invisible, how do we even know they exist? They're like cosmic ninjas or something.
Right.
How do we find them?
It's where the ingenuity of astronomers comes in. They've come up with these really clever ways to detect these hidden objects.
Oh, very clever. So how do they do it?
Well, one way is by observing how black holes influence nearby stars. Imagine a dance where one partner is invisible. We can actually see the visible star being pulled off its usual course by its unseen partner, the black hole.
So it's like we're watching a cosmic pango, but we can only see one of the dancers.
Exactly.
That's pretty cool.
Another clue is something we call accretion disks.
Accretion disks.
Yeah.
Okay, so what are those?
It's like a whirlpool of superheated matter swirling around a drain. And this is kind of what happens as matter falls into a black hole. This material gets incredibly hot,
Okay.
And it emits this intense radiation that we can detect, even across these vast distances.
So it's like the black hole's having a cosmic feast, and
Yeah.
we can see the glowing leftovers.
Exactly.
Makes sense.
But perhaps the most groundbreaking method for detecting black holes is through gravitational waves.
Oh, gravitational waves, I've heard of those, but I'm a little fuzzy on the details.
So they're like ripples in space-time itself. They're caused by these massive events.
Okay.
When incredibly massive objects like black holes collide, they create these ripples, and these ripples travel through the universe at the speed of light.
Wow, so like we can actually detect these things.
We can. In 2015, the LIGO Observatory, they made history by actually detecting these gravitational waves from two colliding black holes.
Yeah.
And this was huge. It was like the confirmation of Einstein's theory of general relativity.
Wow, so we're literally listening to the echoes of these cosmic titans clashing billions of light years away.
We are.
That is so cool.
Yeah.
And there's more, right? I feel like I've also heard that we actually managed to capture an image of a black hole, right?
You're right. Back in 2019, the Event Horizon Telescope, and this was a group of telescopes that were linked across the globe, basically, to create this virtual Earth-sized telescope.
Oh, wow.
They did something incredible.
Like what?
They captured the first ever image of a black hole's shadow.
That's incredible. But how is that even possible? I thought black holes trap all light, right?
Well, they do. But see, they also warp the space around them.
Oh, okay.
So what we see in the image isn't the black hole itself. It's like the silhouette of its event horizon, and it's against the backdrop of this glowing gas that's being pulled in.
So we're not seeing the black hole itself, we're seeing the outline of it because it's blocking the light that's behind it.
You got it. It's like seeing the outline of a void.
That is absolutely mind-blowing. It's like taking a picture of a coin on the surface of the moon.
Mm-hmm.
So we've come a long way in our understanding of these once invisible objects, but I have a feeling there's still so much more to learn.
Oh, absolutely. In fact, some of the most fascinating questions about black holes are still unanswered.
Really? Give me an example.
Well, one of the biggest mysteries is the information paradox.
Information paradox.
Yeah.
What's that?
According to quantum mechanics, information can never be truly destroyed.
Okay, that makes sense.
But what happens to the information that's carried by all the matter that falls into a black hole? Where does it go?
Yeah. That's a good question.
It's a head-scratcher.
It is. So we've got this clash between general relativity, which governs black holes,
Yes.
and quantum mechanics, which governs particles.
Right.
And it's like black holes are right at the heart of this conflict.
They are. And figuring out how to reconcile these two theories in the context of black holes, well, that could revolutionize our understanding of the universe.
It could. That's a lot to ponder. We've gone from imagining black holes as cosmic vacuum cleaners to understanding that they are objects that warp space-time, they possibly hold the key to unifying the laws of physics, and they even have this strange beauty about them. It's pretty amazing.
It is.
And we're just scratching the surface, right?
Oh, yeah. There's so much more to explore.
Well, I'm excited to keep going.
Me too. Welcome back to our deep dive into black holes.
I'm ready for more.
Last time, we talked about what black holes are and how we detect them. Now, things are going to get a little mind-bendy. We're going to explore some really interesting theoretical concepts that black holes bring to the forefront.
All right, bring on the cosmic twists.
Okay, let's start with something called Hawking radiation.
Hawking radiation.
It's named after the brilliant Stephen Hawking.
Oh, yeah, Stephen Hawking, of course. So this idea, it kind of challenges the notion that black holes are these inescapable traps.
It does. Back in the 1970s, Stephen Hawking, he proposed that black holes actually emit a faint type of radiation, and this is due to these quantum effects near the event horizon.
Wait, hold on. Something can escape from a black hole. I thought we said that nothing, not even light, can escape once it crosses the event horizon.
Right?
How is that possible?
Well, to understand this, we have to go into the strange world of quantum mechanics.
Quantum mechanics. All right, let's do it.
So in the vacuum of space, we have these things called virtual particles, and they're constantly popping into existence in pairs.
Pairs of virtual particles?
Yeah, they basically borrow energy from the vacuum, exist for this tiny moment, and then they annihilate each other.
So it's like this constant energy dance happening all around us, even in empty space.
A very good analogy. Now imagine this process happening near the event horizon of a black hole.
Okay, I'm imagining it. What happens?
Well, sometimes one particle of the pair falls into the black hole, while the other one escapes.
So it's like one particle gets trapped and its partner gets flung out into the universe.
Exactly. And that escaping particle, it carries away a tiny bit of energy from the black hole.
Oh, I see. So that gradual energy loss, that's what we call Hawking radiation.
Yes.
Okay. But this radiation, it's incredibly faint, right?
Extremely faint, and we haven't been able to detect it directly yet. Plus, the time it would take for a black hole to completely evaporate due to this is longer than the current age of the universe.
Wow. So we're talking about like a really, really, really long time.
We are. So it's more of a theoretical concept for now.
Okay, but one with huge implications, right?
Yeah,
Because it means black holes aren't eternal. They eventually fade away.
exactly. And it just adds another layer of complexity to our understanding of these objects.
For sure. Okay, let's move on to another mind-bending concept. Wormholes.
Ugh.
Wormholes. I've always been fascinated by the idea of these cosmic tunnels connecting different points in space-time. Is there any scientific basis to this idea? Or is it just science fiction?
Well, wormholes are fascinating. They do emerge from the equations of general relativity.
Really?
Yeah. They're essentially shortcuts through space-time, and they're connecting two distant points in the universe.
So, like, theoretically, you could hop through a wormhole and reach your destination much faster, right? Almost like taking a cosmic shortcut.
In theory, yes.
Okay.
But there are some big ifs here.
Okay, what are the ifs?
Well, first of all, we've never actually observed a wormhole.
Okay, so they're still hypothetical.
Purely hypothetical. And second, even if they do exist, they might be incredibly unstable, like collapsing before anything could travel through them.
So it's more of a what-if scenario than a viable transportation option.
Yeah, for now.
Okay.
Yeah.
But it's still fun to imagine the possibilities. What about the idea that black holes could be gateways to other universes, other dimensions? I've seen that in some science fiction movies.
Yeah, that's another really intriguing hypothesis.
So like falling into a black hole, it might be like falling through a trapdoor into a completely different reality.
It's an idea that's often explored, yeah. Some theories suggest that the singularity at the heart of a black hole could be a point where our universe connects to other universes or dimensions.
Okay, now that is truly mind-blowing. But again, like with wormholes, we're in the realm of speculation here.
Right. We have no direct evidence to support these ideas. Purely hypothetical, for now. But they certainly spark the imagination, don't they?
They really do. They show how black holes push the boundaries of our understanding.
For sure.
Okay, let's shift gears for a bit and talk about some potential practical implications of black holes. I've heard they could possibly be harnessed as a source of energy. Is there any truth to that? Because it sounds almost too good to be true.
It's certainly a possibility, though still very speculative.
Okay, so how would that even work? How do you get energy from a black hole?
Well, one idea is to extract energy from the rotation of a black hole. As matter falls into a rotating black hole, it gets whipped around, it gets whipped around at incredible speeds.
Okay.
And this creates a region around the black hole called the ergosphere.
The ergosphere. That sounds intense.
It is. And within this ergosphere, it's theoretically possible to extract energy from the black hole's rotation.
Wow. So we're talking about like tapping into the power of a spinning black hole.
Essentially, yes. It's tapping into that immense rotational energy.
Okay, that sounds a little scary, but also kind of amazing. Are there other ways to harness energy from black holes?
Another idea is to harness the energy that's released by matter as it falls into the black hole. As that matter spirals inward, it gets superheated.
Okay.
And it releases this really intense radiation.
Okay.
And we could, in theory, capture this radiation and convert it into usable energy.
So we could build like a cosmic power plant around a black hole.
In theory, yes.
My inner science fiction fan is going wild right now. But realistically, how feasible is any of this?
Well, the engineering challenges would be mind-boggling, to say the least.
I could imagine.
We'd be talking about operating in an extremely hostile environment with intense gravity, radiation, and temperatures.
Yeah, that's going to be tricky. So
Yeah.
probably not something we'll be doing anytime soon.
Probably not.
But still fascinating to consider the potential. Okay, what about the idea of using black holes for space travel? Could they help us, like, travel faster than light or even to other dimensions?
That's a question that I think has captured the imagination of a lot of people. The concept of using wormholes for interstellar travel is certainly very appealing. But as we discussed earlier, there are some major theoretical and practical hurdles to overcome.
Right, like, we don't even know if wormholes exist. Even if they do, they might be incredibly unstable. What about, like, using black holes to warp space-time and create shortcuts through the universe. Is that a possibility?
It's another theoretical possibility, but it would involve manipulating these immense gravitational fields of black holes, something that is way beyond our current technology. And even if we could control a black hole's gravity, there's no guarantee that it would create a safe passage through space-time. We don't know what would happen.
Yeah, true. So for now, black holes remain more of a scientific curiosity than a practical tool for space travel. But it's exciting to think about all the possibilities, however far-fetched they might seem.
It is. As we continue to explore the universe and unravel the mysteries of black holes, who knows what we'll discover in the future? Maybe one day, black holes will play a role in humanity's exploration of the cosmos.
Maybe. Well, our journey through the world of black holes continues. I'm ready to keep exploring.
Let's do it.
Welcome back for the final part of our black hole deep dive. It's been quite a journey, hasn't it?
It really has.
From the mind-bending physics to those crazy ideas about wormholes and alternate dimensions.
Yeah.
So much to unpack.
So much.
And now we're going to zoom out a bit.
We are.
We're going to look at the bigger picture.
Yes.
We're going to explore the role that black holes play in shaping the larger universe around them.
The universe as a whole.
I'm ready to see how these cosmic giants influence everything.
Yeah.
Earlier, you mentioned that supermassive black holes are kind of lurking at the centers of galaxies.
Oh, yeah, they're there.
But how do they actually shape the structure and evolution of these vast collections of stars?
Well, think of a supermassive black hole like a conductor, leading a cosmic orchestra.
Conductor, okay.
Its immense gravity, it orchestrates the movements of stars. It affects the distribution of gas and dust throughout the entire galaxy.
So it's not just about things falling into the black hole. It's about this gravitational dance that's happening all around it.
Exactly.
And that dance is influencing the entire galactic structure.
Wow.
Yeah.
It really is. And you know what?
That's...
Their influence goes beyond just holding the galaxy together.
Okay, so what else do they do?
They can actually regulate star formation.
Wait, hold on a second. So a black hole, known for devouring matter,
Yeah.
can actually contribute to the birth of new stars.
They can.
That seems a little counterintuitive.
It does. It's a fascinating balance. As matter falls towards a black hole, it heats up.
Okay.
And it releases this tremendous amount of energy.
Right.
And this energy can sometimes heat up surrounding gas clouds, which prevents them from collapsing and forming stars.
So it's like the black hole's creating a cosmic feedback loop, right? Controlling the rate at which stars are born within its galaxy.
Exactly. Black holes, they're not just engines of destruction.
Okay.
They can also be agents of creation.
Wow.
Influencing the evolution of their host galaxies in some really profound ways.
Okay, and you mentioned earlier those powerful jets of particles and radiation that some black holes launch out.
Oh, yeah.
What kind of impact do those jets have on the surrounding environment?
Oh, these jets are incredible. They can extend for thousands of light years, and they're blasting out these high-energy particles almost at the speed of light.
Wow.
And as these jets, they plow through surrounding gas clouds, they heat them up, they create these shock waves, and these shock waves can actually trigger star formation in some areas
Wow.
while suppressing it in others.
So they're like cosmic sculptors,
They are.
shaping the distribution of gas and stars throughout the galaxy.
Exactly. And these jets can also transport heavy elements that have been forged in the hearts of stars far beyond the galaxy where they originated.
That's incredible. So black holes are not just about destruction. They're also contributing to this like cosmic ecosystem.
Yes.
They're seeding the universe with these building blocks for future generations of stars and planets.
They are. They play a crucial role in this grand cosmic cycle of matter and energy.
Right.
They recycle matter, they convert it into energy, and then that energy influences the evolution of galaxies and ultimately the universe as a whole.
It's amazing to think that these objects that are born from the death of massive stars can have such a profound impact on the universe around them.
Isn't it?
They're like cosmic engines, driving change and evolution on a grand scale.
They are.
You know, we started this deep dive imagining black holes as these terrifying cosmic vacuum cleaners. But we've come to see them as so much more.
Oh, so much more.
We've seen that they're objects of extreme physics, they warp space-time, they challenge our understanding of the universe, and they might even hold clues to unifying some of the most fundamental theories in physics.
Yeah.
It's been an incredible journey of exploration and discovery. And even though we've reached the end of our deep dive, I feel like this is just the beginning of our fascination with black holes.
Oh, for sure.
What do you think?
Black holes remain one of the most fascinating and challenging frontiers in astrophysics. They really beckon us to explore further and to try to unravel those mysteries that they still hold. It makes me wonder, if you could travel to the edge of a black hole, what do you think you would see?
Yeah. It's a question that's captivated scientists and dreamers for, like, generations.
It has.
And as we continue to push the boundaries of human knowledge and exploration, maybe, just maybe, one day we'll have an answer. But until then, keep looking up, keep asking questions, and never lose that sense of wonder at this vast and mysterious universe we call home. Thanks for joining us on this incredible deep dive.
It's been a pleasure exploring with you.